Ladies and gentlemen, please welcome to the stage Constant Bridon.
I'm Constant, I'm French, I live and work in Paris. I'm a consultant in a cabinet in Paris specialized in data science. And at the moment we're mainly interested in industrializing data science solutions. This is not really about work, this is more a toy. Actually, I was working last year on an autonomous toy car. That is a really small car that is supposed to be autonomous thanks to a camera and deep learning. And I thought it was really interesting because this is like real-world machine learning on a small machine. So I would like to share it with people coming to the conference. That's cool. All right. We're good to go. Could you hear anything I said before on the video because it was really low? Hopefully not, because I'm going to start with the same stuff. Thanks for coming. There's quite a lot of people. So I know the last thing is standing between you and lunch, so I'll try to make it quick. And also because we are in a theater, and it's a really great idea, guys. Thank you for the organization. I'll try to make it entertaining. All right. So today I'm going to talk about an autonomous toy car. So huge disclaimer, it's a toy car. Unfortunately, I couldn't take it with me on the plane. So just to figure it out, it's a car that big, right? I'm not trying to compete with Tesla or Google or whatever. So before starting, quick words about me. If you haven't heard it in the previous video, I'm currently a data scientist at Octo Technology. And being a data scientist has absolutely no meaning today because I'm pretty sure that everyone in this room is self-defined as a data scientist. So I find it funny because you realize that it does not mean the same stuff. In my company, it means that we're mainly focused on algorithms, math, stuff like that. So we need to understand those, but also the data architecture and how it works in information system. And the last part of it, the last axis, is customer understanding, because I'm a consultant, and if I don't work for someone, I don't work at all. So to put it differently, now I'm mainly interested in industrializing data science solutions, and it needs to be defined to have some sort of meaning. So I've witnessed in the past 3 years that actually data scientists are becoming developers. So they are working now with developer tools. And it's no, this is a small joke. A couple of years ago, I was just using Jupyter notebooks, no test, just running junk codes and trying to do proof of concepts. And just to show that a model is possible and there's value out of it. But then it wouldn't go live because it was not possible to use it the way it should be used in a company. And now I'm more using these kind of tools such as Jenkins, Docker, and PyCharm if you're working with Python or IntelliJ. Which means that actually data science is code. So it needs to be done the way code has been done for the past 30 years, right? So last year I was already in Big Data Vilnius. I made a presentation about interpretation of algorithms and especially ensemble methods and more specifically gradient boosted trees. And I'm really happy to be back again to talk about something else that's probably a bit more fun, but so this talk is going to be, well, that's big. This is a work in progress because it's something that I'm working on my free time. So I'm expecting as much as you are from this presentation. I want questions, I want criticisms, I want feedbacks, whatever you wanna do. There's also something I want to say. I had this presentation a couple of months ago in London at the ODSC, Open Data Science Conference. And there was a guy in the room who was really interested in doing this in his own country. And actually, he's going to start it next month. So if you're interested in doing this too, just hit me with an email or just ask me anything after the presentation. I'll make sure to make time for you. So I'll talk about the initiative itself. It's not about me working on an autonomous toy car. This is a competition held in France. And in this competition, I had several stuff I wanted to try, and especially data simulation for training the model in the car. and I want to share with you the difficulties and experience that I've withdrew from this journey. So this car and this autonomous car is part of a competition that is named Iron Car. It is actually named after a competition that was held in the US a couple of years ago that was do-it-yourself robot car or something like that. So in France, it is organized by non-tech people. That is quite important because they don't really understand what's going on, but it's also really funny to see that people not in the tech industry and not in the AI industry are trying to, generate communication around artificial intelligence. So the why of the competition is pretty clear. They wanted to help French data scientists to become a reference in the country and outside the country. So they needed an event to have some sort of popularity. Have promotion in France about artificial intelligence. There's a huge report from the government a couple of weeks ago saying that France is supposed to be a leader in Europe in artificial intelligence. So hopefully we'll thrive for it. And also help people to have like a real-world machine learning problem with constraints, gentle constraints, because most of the time it's just toy examples. Well, this is a toy, but it's not a toy example. And stuff running on real hardware. So it started in January 2018. The last race of the year was last Saturday. So it's roughly a year. It's been roughly a year I've been working on this. We had 8 different teams in the deep learning track. So that many different cars and different solutions and different approaches. And it was open to anyone, students, professionals, freelancers, whatever. So it was really a community building around like a game. So it was really interesting. The rules for the competition are pretty easy. So the first one is it needs to be affordable because it's open to anyone. So the students must be able to take part of the competition. It means that basically with the car and the electronics and everything you need to use, it does not go above 500 euros. Because if you put a LiDAR on the car that is like a radar with light, it's pretty easy just to grasp everything that is happening around and make a decision out of it, but it's pretty expensive too. The rule number 2, and it's been formulated by the non-tech people organizing the competition, is it needs to have deep learning in the decision process. So basically it means nothing. So the competition itself was not really about winning or competing. It was just trying to use deep learning techniques to see how far we can go with the constraints that we apply to ourselves. So throughout the year there were 2 types of races. The first type of races was training. So we had access to the track, trying to get some data, trying to test our algorithms and stuff. And competition races, 4 of them throughout the year, with a ranking solution, to make it a bit challenging and to compete against each other. So the car is supposed to drive alone on the circuit, so there's no different cars, just alone on the circuit, within the lines for a total of 3 laps in a minimum amount of time. So it means that you have your car, you make the 3 laps, it's probably like 5 minutes or whatever. The next one is 2 minutes and 3 seconds, so he's the first, and so forth and so on. So I'm really proud to say that I'm the last in general ranking. There are different reasons for that. Probably because I tried to address the problem with a specific solution that I designed myself, and actually it was really time consuming and probably a bit too ambitious, but I want to share it with you. First and foremost, because this car, in autonomous toy car, we're going to talk about the car. The model that I used is actually this one. I bought it online. I think it's 300 euros roughly. So there's already a battery here that is serving energy to the front wheels and the back wheels for respectively speed and direction. This is the 3D printed structure that we used to put all the electronics on it. So you can see here there's some sort of a pole to put the camera on. We needed an external battery to supply energy to the different electronics that we're using, because we didn't want a car to run out of energy during a race. And because it was not running, I spent a lot of time pimping the car just to make sure that if it doesn't run, at least it's beautiful, right? Remember that I'm French, so we're all about vanity. Right, so I've said that electronics is encompassed, embedded in the car. So the electronics is pretty easy if you go through the decision process from the image to the command. So the image is taken by the camera as a streaming, well, the video is taken by the camera as a streaming images. It's a 60 frame per second. And so the camera is streaming this images to the Raspberry Pi here through Python libraries. So in the Raspberry Pi there are already Python objects, and namely NumPy array. So the Raspberry Pi is responsible for making the decision with the deep learning algorithm. So it outputs a command such as 30 degrees right, 20 degrees left. And I decided to use an Arduino hat here that is plugged into the Raspberry Pi on the GPIOs, because actually the command to the servo motors are analogous, and the Raspberry Pi is only outputting a numeric value. So there's actually a way to work around this and create the real command to the servo motors with the Raspberry Pi, but actually there is a Python library designed with this hat that makes it for you. So it was more of a, it's not mandatory, but it was more of a shortcut, just to, I didn't want to go too deep in the hardware, and I didn't want to go with real signals to control the servo motors. And then you have your command served to the motors so that you have the direction and the speed. Okay. The core of the reactor, this is the software, so it was just a global context. But now what is really interesting is that the command, well, the only thing that we're trying to predict is the command. It was something, some sort of a simplification of the problem, but actually it's pretty hard to also take into account the speed. So I decided to just take into account the command and make the prediction about it. So the car is supposed to ride at a constant speed, so it's not really fast. You'll see afterwards, but it's fast enough to be interesting. And because we're dealing with the streaming of images, video, the deep learning architecture is mainly about CNNs, because they're pretty good dealing with those type of value, especially with small computers such as Raspberry Pi. Then the command in angle, because actually the command that you provide your servo motors is going to be a certain amount of degrees on the right or on the left. I decided to split it into 5 quadrants here, because actually CNNs are way more efficient with classification than in regression. Actually, we tried it. It worked a bit, but classification was way faster and easier to design. So we decided to say, well, the first quadrant here is going to be the far right command, and then the second is going to be a bit right, and then third is straight ahead, fourth is a bit left, and so forth and so on. You got it right. We need to make a calibration of those 5 quadrants regarding the different threshold that we provide the servo motor with. So there's actually a good talk about it in PyData Amsterdam 2018 by, sorry if I got the name wrong, Niels Zeilenmaker. If you want to check it out, it's pretty neat. And that's it. So we have everything set up, and so we are working with real-world data. And actually, the first teams, what they did, and it's pretty easy to do, is just I take my car, and this is actually a remote-controlled car, so I can pilot it, right? So I just put it on the track. I pilot it a couple of laps, and I'm pretty confident on the way I'm piloting it on the track. And so after a couple of laps, I decide to record the data. So every second or every half second, for example, I take a picture and I take the value that I have on the servo motors, right? So it's pretty easy to generate the data set like this, and you already have a labeled data set, so you can feed it straightforward to your deep learning architecture. So what is wrong with such an approach? How many of you are really happy with this approach? Raise your hand if you're happy with that. Oh, come on. Right, thank you. Well, I will explain you why I disagree with that. But actually, the guys who won the competition did that, and I did not. So the real problem is, if you do so, if you record the way you're piloting on the track to generate your data set, what are you really trying to do? You're not teaching your car to drive, you're teaching it to drive the way the pilot is driving it on a specific track. So there's some sense of overfitting coming here. The thing is, if you just, for example, if you're a bold pilot, you're going to try to cut on the different angles and do stuff that you can do because you're a good pilot. But if you're not, maybe you're going to be slower, so you will have different directions and different trajectories. And so the problem I had with this approach is that the model does not generalize, right? If my data set, even though I have a couple of tracks, if my data set is only me driving the car on those tracks, what I did training and feeding my deep learning architectures with those data is just telling the car how to drive the way I do, not making the decisions for herself. All right. Actually, this is what is called shaping in a short note of Andrej Karpathy. Andrej Karpathy is the head of research at Tesla. He's also really famous for his explanation of CNN architectures and a bit of LSTM too. And I think it was 2 years ago, he made a short story that is named A Short Story of AI, a Cognitive Discontinuity. And there's a link at in the presentation. I strongly advise you to read it. It's really interesting. And actually, in the story, he says that in the near future, there's going to be a specific job that is to take control of the machines and have them do a specific task. And as it learns how to do the task, you just release a bit of the control that you have on the machine, and you give it a reward if it does the job well or not. So this is just the example in the story is just you know, carrying tables and chairs. And so in the first iteration, you just have the full control on the machine. It's just like in acquisition mode, trying to understand what you're trying to teach it. And so you carry the chairs and the tables, and slowly you just release the control and just tell it to do how it's supposed to. Well, you don't tell it to do how it's supposed to do, but you just give it reward if it does the task that it's supposed to do. So this is shaping. This is really interesting, but there's nothing about intelligence in the sense, because this is just do as I say and don't try to find the right pattern in what you're trying to achieve. And actually the example is quite simple. This is the type of images that my camera is seeing when it's on the track, right? So this small board here is just about calibration. We can have a word about it afterwards. But you can see that actually you see the lines, the side lines here, the central dashed line in the middle, but you can also see a pillar here. And there's even someone walking in the background. And on the track here, the car is supposed to go, for example, 45 degrees on the right-hand side. But if you feed it to CNN architecture, you don't know if the model itself is making the decision because it has seen those lines, or because it has seen someone walking in the background, or because of this specific pillar. And actually we had the example. On the track we had like a construction cone, you know, this big orange stuff, marking the beginning of a direction. And all the teams acquiring data were taking pictures with the cone. And actually when we decided to do the actual race, they moved the cone away on another spot in the track, and all the cars were completely messy in this specific spot. So maybe they made the decision to turn right because they saw the cone and not because it was supposed to turn right. So at that point, I was wondering if it was possible to generate the training data in the sense that I want to have a physical behavior, something that is that has meaning in the driving process. And also I tried to have the challenge to have a car in a box, never driven on any track, and is it possible to drive on any circuit outside the box right away? Once again, pretty ambitious. Disclaimer, it didn't work. So, because I wanted to generate the data, I wanted to have some sort of simulator. So I'm a developer, but I'm not a good developer. So whenever I have to code something, what I do, I go on Google or on GitHub and I see what's already out there. And actually, there was a simulator available on GitHub, and it's actually from someone who is in the competition now, Vincent. And so what he proposed was to take a couple of ground images, like colors and textures for the ground. You can just have this type of output from the simulator, which is the lines that you have and the command that you're supposed to have in this specific spot. And you can use those simulated data to train your model. Oh. So that's what I did. I trained the model and I deployed it on the car, and here's what happens. So first and foremost, you can see that the car is moving upward and stops, upward and stops. So the thing is, it's actually, the speed is so slow that it needs to buffer a bit of energy just to go over the friction. So it's pretty easy for me because I have a lot of time. Remember that we have 60 images per second. So the slower it is, the more images I have to make my decision. And you can see that at the end of the track, the car completely fades away and goes out the track. So it's not really good. But I don't really understand why. If you go to those images, for example, so you have the command in radian, so it's basically the same as degrees. And so it says here, you're supposed to go 0.13 radians on trigonometric, well, anti-clockwise, say. And so it's kind of weird because it means that it needs to go left, whereas the lines are going to that direction. So it started, I was, how come that it's supposed to go left and the lines are going on the right and the car is supposed to go on the right? So it was the first question I had. And actually what I thought was, well, maybe the car is outside the lines in this specific position. And so it needs to go left to go inside the lines and then to have the right direction. So I kept going with this simulator, and the model that we trained was actually pretty good. We decided to use it to train the model all the way through from scratch because it's actually a simple model. We considered using transfer learning with the ConvNet or whatever, but remember we're working with the Raspberry Pi, so the goal behind it is not to have the huge model that Google outsources. And so it's pretty easy actually. You have 4 different convolutional layers, and for a total of roughly 5,000 different parameters. And with the generated data that we used, we had a 94% accuracy. So this is MultiClass classification, so you need to understand that 94% accuracy for a multi-class classification problem is huge, because on a binary classification is good, but when you have 5 different classes to predict, you have way more possibilities to get wrong. So only after 40 epochs, it was already pretty good, and actually the overall pipeline was good, right? We made training data, validating data, test data. So there's no overfitting possible. So the only explanation that I had at this point was, well, actually we're training on data that are not the right representation of the type of data that we have when we're live, when the car is on the track. And actually that's the problem. So if we go back to the simulator that we used, how an image is made, it's just you take the ground, you just draw a middle line and side lines, and you apply a trapezoidal perspective that is completely arbitrary. It was actually funny to find it out in the code. And then you crop it like it's art. So you have something that is completely cut because of those black parts of the perspective. So I realized that the perspective itself was the problem. It's pretty easy to actually generate those lines, and from those lines gain the command, but I had to work on the perspective. So I decided to work on my own simulator. I'll try to speed it up a bit. And so say this is a picture seen from above, that my car is somewhere on the track. So I can set that my car is here and it's looking at the direction. All right, thanks. And I can compute from this specific position, knowing the dashed line in the middle that is not printed here, but knowing this dashed line in the middle, I can have this command here saying you need to go back to the central line, right? But having this, is it possible to have like the real image that the car is seeing on the track? So you need to apply the right perspective to this specific image to have what the car is seeing right away. And so this is when it starts to be a bit painful, because I wanted to do it in Python, so I needed to go back to how a camera is seeing images and projection and stuff. So this is time for a bit of algebra. So what is actually happening when the camera is seeing you? So for example, this camera over there. So if I'm holding this remote here, I can set, arbitrarily speaking, a point to be the origin of the real world coordinates, saying, for example, the point in the room there. And so that's the remote would be my object here. So what happens is, in the pinhole camera model, that is the one that is used when you have like regular cameras, this point is projected in the image plane. So this is the rectangle that you have here with the perspective. And you can actually compute the coordinates of this point in the image plane, given some values from the camera, and given the position in the real world. So I thought it would be possible to do so, and actually it is. This is exactly what I tried to explain to you earlier. So the coordinates in the image plane here are just a combination, a linear combination, because those are matrices, so products of matrices. So those coordinates are actually the coordinates in the real world that I can set. Once again, I can say that my remote is here, and I say it's like 5 meters away from the origin. And I can just use what we call the intrinsic parameters of the camera, that are the focal distances, the different weights. The focal distances are the way the image is transformed by the different axes. So how much it goes as a loop, an expanding camera or not on the given axis. And those points here are actually the center of the image plane. And I was pretty happy, because the last one here is just the camera position in the real world coordinates. So this is namely where it stands, and what are the different direction on this axis, and this axis. So just a rotation matrix here and a translation matrix here. I was like, yeah, it should be working, no problem. So I said, well, this is what I want to have. The zooming effect here is actually a constant, so we don't really care about it. So the intrinsic parameters, remember the chessboard that I had on the floor on the picture I showed you earlier? Well, this is exactly what it is used for, because you know the different values of the squares that you have on the chessboard, so that you can just compute those values, the focal lenses and the center of the image. And I said that this, I can set it. I can just set arbitrarily the real world coordinates. So you can see it coming, because I swapped over it. The real problem is to determine actually the extrinsic parameters. It was really cumbersome to do so in Python, because you have the image as seen from above, but it is already an image, right? And I want to apply the perspective on this image and not on a real world object. So I need to have the coordinate of a real world object, say the track in front of the car, and I need to apply first the transformation from the real world coordinates to the coordinates of the picture as seen from above, and then apply the transformation. So I can see you all frowning. It's pretty hard, and actually it doesn't really work in Python. So at that point, I decided to use a 3D engine rendering because I was looking at how it is done in the video game industry, and it's pretty amazing. Those tools are pretty amazing, and I think there will be a huge part of machine learning techniques in the next years. For example, Unity is basically what does POVRay. So this is an open source tool, and it can use actually the UV mapping technique. So this is basically, you create a box. So a box is 6 panels. So you have the panel at the bottom, the panel at the top, the front, left, right, and back. So you create it this way as a plain image. And you say this is a box, so you fold it as an origami, and you place the camera inside, and you just tell me what my camera is seeing. Well, when you define the camera, you just say, well, this camera is the intrinsic parameters I mentioned before. You can provide them to PovRay, and actually you can say, within this box, my camera is here. Tell me what it's looking at and what it sees. And it's pretty amazing because I put it here because it's just voila. It's just, if I'm only considering the floor, the bottom panel here, so the yellow cross is actually the position of my car. The red dashed line, maybe you can't really see it, but the red dashed line here is actually the direction of my car, with 18 lines of code as a JSON object. I have this type of rendering. Okay, so those lines are actually, my camera is an ultra wide angle. This is the type of camera I'm using on the car. It's placed at this specific points. It's looking at this specific point, and you just apply the texture of the image to get what it sees. All right. So how could I use that to generate my data for learning? Well, first I realized that you have 2 different type of lines on a track: straight lines and curved lines. So I wanted to be as general as possible. So I decided to split those cases into 2. And also so if it's not clear, this is the bottom, this is the one I'm trying to use, so this is the same thing here. So I can generate those lines, but I decided to put my camera right in the middle here, facing straight forward. And it took me a bit of time to realize it, but actually this is the easiest way to take full advantage of the POV ray tracing algorithm, because if you put your camera looking at that direction, actually, because I don't want to have all the panels, well, there would be a blank here, and it's not really suited for my problem. And also, because I'm able to, trace any line, any line I want, actually every position on the track can be approximated by such an image. I just need to bend the lines one way or another. So I was pretty happy. And for straight lines here, so I have the central dashed line in the middle. So in order to compute the command that is going to be used to supervise the learning of the algorithm, I just say, I set my car to be here, and I know that this dashed line is here. So my command is, starting from this point, I want you to go to, say, 30 centimeters alongside this line. All right. So I have the vector, I have the starting point, I have the end point. So I can say your command is this one, and physically speaking, it's going to be a command, go 30 centimeters away, right in the middle of the track. Curved lines actually are quite the same too. Well, they're harder to draw actually, because you need to define starting point, end point, and a radius. But actually, it's pretty easy to do too. The only difference is about the command itself. So this is not alongside the straight line, so this is alongside the arc, but it's the same. I tell my car to go 30 centimeters away alongside this arc to be the command. Right, so I'm pretty happy about this. I can have, in this example, 2 images with 2 different commands to feed my algorithm. So how do I do to have 50,000 different images to do so? Well, I just set it to have straight lines and curved lines, and I just change a bit of parameters. So going from this to this is just starting point and end point are here. For this one, starting point and end point are here. Same goes with curved lines, and actually I can generate those pretty easily. A quick note here, you might notice that actually all the lines are going to the right hand side, but it might be that the car needs to go left. So what is really interesting with this approach is that there's there's physics and geometry about it. So by flipping the image, right? So just switching it around and conjugate the command by pi, which means if here my command, for example, is 20 degrees, and I say it's 180 degrees minus 20 degrees, right? Conjugated by pi. Well, I have another data point to train on. And it's actually one of the methods that you use when you want to do, for example, data augmentation. When you want to have a cat detection algorithm, you just take the same picture of the cat, but you flip it or you crop it. So I was really, really happy with this small trick. So here it goes. This is the type of images that I have. So how do I industrialize the production of those images? Well, I designed, the code is actually available on my GitHub account. So I have a configuration file setting the line width. So if it's really large or not. The dash length, because there's always a dash line in the middle of the track. So what is the length of a given dash? The line spread, which is how large is actually my track, which is strongly linked to the pixel to centimeter value, right? So on my image, I say, for example, that a pixel is 0.3 centimeters, for example. So those are parameters that I need to play with to find the right value for my data generation, and all other different parameters such as the line colors and stuff. And so I take a bunch of pictures of the ground. When I arrive at the competition, I just, for example, this is a good example. The floor was like this last Saturday, but before that it was concrete. So the color is different, the texture is different. So I just take a bunch of pictures on the ground. And I took those pictures as the starting picture for my data simulation. For the moment, and that's a shame, it's only on a notebook to generate those data. But I'm really looking forward to having something that is more industrialized. And also a problem is because I was training on AWS, well, on the cloud, sorry, no advertisement, but I was training on the cloud. So there's a need of a significant space for the memory for the different images. So those images here are like 52 KOs, so you need to take this into account if you want to have thousands and thousands of images. It can be a bit cumbersome. So what is next? Well, I started it, but I still want to go all the way through regarding the industrialization of the data, because now it's just a notebook and you don't have it. And my goal is for you to have it and play around. Share the code, so you can go on my GitHub account, and it's at the beginning of the presentation to see how it goes. Play around with POV rate, which is amazing. I mean, if you're really working with the images, this is a tool that actually blew my mind. Test different approaches. So I mean, for example, in the UV mapping technique, I can put different stuff in the box. For example, people or cylinders in the middle of the box, and say, well, as seen from above, it's just a circle, but when you render it, it's a cylinder, for example, 2 meters high, so that to see if the model is robust to noise generation. And print another structure too, but it's not really the point of the talk here. It's more about machine learning. But of course, there was a presentation in this room about reinforcement learning in AlphaGo before. Of course, if you've seen it, you can see it coming. Is actually using reinforcement learning to teach the car how to drive, which would be the best way to actually have a model predicting it. So the real problem about the reinforcement learning is also simulation, but you need to have all the physics of the car encompassed in the simulation, which is really hard. And those guys, actually Chinese people, they had it, but only to have collision avoidance and obstacle detection. And actually the simulation here, the car cannot really speed up. It's just at a constant speed and tries to follow a line and try to avoid any obstacles. But check this out, it's pretty cool. And this is also what I will trying to do for the next year, because it's been said that Iron Car is going back to France next year. I hope you guys in your I think there's 17 different countries represented in the conference. I hope you guys want to try it at home too. I'm good with the talk at this point. Before the questions, I will do just right before. In Octo Technology, we have what we call the return on time invested. So I'm going to take a picture of the room. You're going to raise one of your hands, and you're going to mark me from 1 to 5. 1 being you've lost your time. 5, you couldn't have been in a better place. 3 is just, meh, that's good. You good? So I count to 3. 1, 2, 3. Awesome. Thank you very much.
So do you have any questions for Christian?
Or maybe on the... Is there a question in the room? I can't really see with the lights.
No. So
Maybe we can go straight to the...
yeah.
All right, so I'll just take them the way they come. All right. So what would be the biggest challenges trying to transfer these concepts to a real car? Well, I mentioned it at the beginning. Actually, the algorithms that you have in a car, such as Tesla cars, is actually not just one algorithm. There are thousands of them just specialized in collision detection, in other cars detection, in line detection and stuff. So the biggest challenge would be to have different algorithms with different targets. Actually, the first target here is just to stay right in the track, in the middle of the track. Actually, those cars are equipped with way more algorithms than the ones running on a small Raspberry Pi. But actually, there's no real challenge. If you want to go with reinforcement learning, you can do it with a real car. You just need to have the physics of the car, which is how much can it turn right, how much can it turn left, what's the max speed, and how does it accelerate, for example. The real problem with machine learning algorithms put in a car is when it goes bad, right? Who's responsible? That's always the problem. It's the same in health, right? We have really good algorithms to detect cancers, to detect anything we need to detect. The thing is, if one time it is wrong, well, who's responsible? Who's to blame? And actually, that's why we still have doctors, so that we can blame them when it goes wrong. How long did it take to train the model? What kind of infrastructure has been used? So the model is pretty easy to train. We decided to start from scratch because there was no point using transfer learning on CompNet, for example, because the pattern that we need to detect is pretty easy. We're not trying to detect, for example, I don't know, cats, dogs, or whatever, where the patterns are really, really specific in the needs. Well, the patterns need fine-tuning, so we decided to have a small architecture with 6,000 parameters. Sorry. So it takes actually for 100 epochs, it takes less than 10 minutes on a specific architecture that is on AWS. We've used P2X large machines on AWS, so it's pretty neat too. You have an open AMI using Python and deep learning, so you can just pop it up and run your code on it. So it's pretty easy in this point. Once again, because the architecture is really easy, because the pattern is really easy too. Can the symmetry of the problem be exploited directly in the network model? Wow, good question. I think it could be if we're trying to have a model taking into account the previous decisions and the next decisions. The main drawback of this approach is just like an image is taken as another, so there's no continuity in the command. And so when the car is driving, you can see it on the wheels. It goes either straight or completely right or back straight. So it's not really a smooth command. So the next step is to use these type of approaches to take it into account, and maybe we can exploit it directly in the network. But in this specific setup, there's no point, because actually in the training process, an image is going to be taken as another image, even though it's not the next image that the camera is going to see on the streaming when it's running on the track. So maybe I'll have it a look, but it's more about playing around with this stuff, but I'm not sure it's really useful for the algorithm itself. Do we still have time? Cool. How did you obtain images from above? Well, I create them. So I just take a picture of the ground, and on this picture I decide to draw lines with actually OpenCV on Python. So I draw the lines, and then I have my picture from above because I can set my camera to be in a specific place and looking at a specific direction. So that's the whole point of it, is just to simulate the data from nothing and actually just a couple of pictures of the ground. I don't know if it answers all the questions, so if you have something I want to elaborate on, you want me to elaborate on, just raise your hand. Where can we see video of the race? On the website Iron Car. So we have a couple of videos. Actually, we went on TV on a Sunday evening at 8 o'clock, so it was pretty nice. You can see them there. You can also see the videos from do-it-yourself robot car in the US. It's all online. Just go with autonomous toy car.
So this is all the time we have.
Cool.
Thank you, Constant.
Thank you very much.
And we have a little gift for you.
Oh, thanks. Thank you.